So in this video, we're going to look at what happens to delta G when we change the pressure or the molarity of our reactants and products. When we calculate delta G0, this is for when all reactants and products are at 1 atmosphere for gases and 1 molar for solutions. What we're going to do is see what happens when we change those pressures and molarities. Delta G is when all reactants and products are at 1 atmosphere or 1 molar. This is the delta G we've been calculating so far. Delta G is what happens when we change some of these molarities. Okay. R is 8.31 joules per mole Kelvin, temperatures in Kelvin, and Q, remember, is our KEQ expression, but not necessarily at equilibrium. Okay, so products over reactants raised to their coefficients. So let's just look at a couple of problems. One method for synthesizing methanol involves reacting carbon monoxide and hydrogen gases. There's the equation. We want to calculate delta G at 25 degrees Celsius for this reaction, where CO gas is at 5 atmospheres and H2 gas is at 3 atmospheres, and we convert them to liquid methanol. First, let's go ahead and use these delta G's of formation to find the delta G for this reaction. Okay, so delta G, remember, it's just products minus reactants. So products minus 166 minus the value for CO minus 2 times the value for H2. So we get a value of let's try an example. For instance, we're going to synthesize methanol from CO and H2. The CO is going to be at 5 atmospheres. The H2 is going to be at 3 atmospheres. And I've given you some delta G's of formation. So first, let's find delta G. Remember, that's equal to the delta G's of formation of the products minus the reactants. So we're going to say delta G0 is our product methanol. So minus 166. Sorry, I forgot to stick this in the table before. This is minus 137 here. Minus the CO, which is 2 times minus 137. For Christ's sake. For example, one method of synthesizing methanol involves reacting carbon monoxide and hydrogen. There's your reaction. And we want to find delta G at 25 degrees Celsius when CO is at 5 atmospheres and hydrogen's at 3 atmospheres. And we've given you the values for the delta G's of formation. So first thing we're going to do is find delta G0. So remember, this is products minus reactants times their coefficients, right? So delta G0 is going to be the methanol, which is 166, okay, minus the value for CO, minus 137, minus 2 times hydrogen. So if you do all of this together, we're going to get a value of negative 29 kilojoules, or negative 29,000 joules. Okay, then what we're going to do is we're going to plug it into our equation, right? Delta G is delta G0 plus RT ln of, so Q is going to be 1, because our methanol was a liquid, we don't include that, over the partial pressure of CO, right, times the partial pressure of hydrogen squared. All right, so when we start plugging in here, we do minus 29,000 joules, because R is in joules, okay, times 298 Kelvin, times the ln of 1 over, let's see, 5 times 3 squared. All right, so that's going to give us negative 29,000 plus negative 94.27. That's going to give us negative 38 427 joules, or negative 38 kilojoules per mole of as the reaction's written. Okay. To do one more now where we change some molarities, let's find delta G for the reaction where HF goes to H plus F minus. The H plus and F minus are 0.78, the HF is 0.24. So delta G is delta G0, RT, ln of this, and we're going to give you the delta G0 for this as 18 kilojoules, okay, rather than taking the time to calculate that. So we plug in our equation, 18,000, because we want it in joules, plus 8.31 times the ln. Okay, so this is 0.78 times 0.78 over 0.24. Okay, so 18,000 plus 2303 gives us 20,304 joules, or let's call it 20.3 kilojoules per mole of reaction. So there's a couple of examples using this.